This is part 2 of the video notes for Objective 4B, solving systems with augmented matrices. In this portion of the video notes, we're going to practice the row operations required to bring a matrix into reduced row echelon form. So our first example is simply to follow operations that have been provided to us. So we have a matrix that's 2, 3, 7, 1, negative 1, and 1. And the first set of directions say R1 equals R1 minus R2. So in the beginning, we say where the answer is going to go. This means that we are going to replace row 1. So our answer will have the same row 2, but new numbers in row 1. Then we have the operation being performed. We want to do R1 minus R2. So we're going to do 2, 3, 7 minus 1, negative 1, and 1. Remember that each pair has to be subtracted. So 2 minus 1 is 1. 3 minus negative 1 is 4. And 7 minus 1 is 6. The next step that we're being asked to compute is to replace row 2 with row 2 minus row 1. Since row 2 is being replaced, row 1 will not change. Row 2 is 1, negative 1, 1. We're going to subtract 1, 4, and 6. 1 minus 1 is 0. Negative 1 minus 4 is negative 5. And 1 minus 6 is also negative 5. The next step is to take negative 1/5 times R2, which is also the same as saying R2 divided by negative 5. This means that R1 will not change, and R2 will just be divided by 5. Problem is R1 equals R1 minus 4R2. So R1 will be replaced and R2 will stay 0, 1, 1. We're going to write R1, 1, 4, 6, minus, and 4 times R2. 1 minus 0 is 1, 4 minus 4 is 0, and 6 minus 4 is 2. This is the final answer for following the steps required in the notes. Row echelon form. Now, when we're solving a matrix system, we're looking at a 3 by 4, but we're only focusing on the 3 by 3 values representing the coefficients of the variables. So the process that is recommended for solving is so that you don't undo steps. Ideally, we're going to fix column 1 first. So to fix column 1, we're going to try to get a 1 in the top left corner and zeros below it. As a word of advice, if you are attempting to fix if you're attempting to fix column 1, or when working on column 1, each of your operations should rely on row 1. All of your formulas should include row 1. Then we want to get row 2 settled, or column 2 settled, so we want to try and get a 1 in the center and a 0 above and below. Now, the 1s down the diagonal are your last focus. It's very nice to have a 1 in this position because you can use this to fix the other 2 rows. However, this could be a 2, a 3, a 4, a 5, all the way up until the very end when you write your solution. So if it's a choice between having a 2 right here and having 1/2 or fractions in your matrix, leave this number as something other than 1. The zeros are critical in the beginning. The same advice holds. If you're trying to get a 0 here or a 0 here, this is column 2. If you're trying to fix column 2, all of your operations, all of your steps, should utilize row 2, because row 2 is where the number is located. Row 2 will help you eliminate the values in column 2. And then lastly, when you're working on the last column, and this should be the last column that you work on, you're going to be using R3, this last row, which will actually be done by the time you get to column 3. And you'll use R3 for your operations in order to get zeros in column 3. So with this in mind, you want to start with column 1, then move to column 2, and then move to column 3. The zeros are non-negotiable. You have to have zeros in these locations. However, the ones can be any number until you're done solving the problem. For example 4, we're going to use row operations to solve our first 3x3 system of equations. And we're looking at the augmented matrix here. And so we want to follow the strategy. We want to fix column 1, followed by column 2, followed by column 3. To fix column 1, we need to get a 0 here. And we can see that 1 minus 1 would make 0. Since we're in column 1, we really want to use row 1 to help us make 0. And we'll do row 2 minus row 1. Then we want to make a 0 here, and if this were the elimination method, and we were just focusing on the first two rows, or the first row and the last row, we would need to multiply this first row by -3, so that -3 plus 3 would make 0. To write that in row notation, we say row 3 is equal to row 3 minus 3 row 1. This will get us the 3 minus 3 here in this position. Underneath my matrix, let's copy down row 2. We have 1, 2, -3, 4. And then row 1 is 1, 1, 0, 1. And we need to subtract these rows together. 1 minus 1 is 0. 2 minus 1 is 1. -3 minus 0 is -3. And 4 minus 1 is 3. This row will now be the new row 2. And the benefit to using the whiteboard is that I can just replace this row myself. Repeat that with our second operation. And our second operation is to do row 3, 3, 0, -4, -6. And then instead of doing minus, I'm going to do plus, and I'm going to distribute the -3 to each term in row 1. So we're going to do -3, -3, 0, -3. That's going to give us a new row 3 of 0, -3, -4, and -9. When I go to copy this row down, I'm going to go ahead and change the signs so that they're all positive. And that gives me 0, 3, 4, and 9. And over here on the side, what I've basically done is switched my subtraction around so that I did 3 row 1 minus row 3. Now that we're done with column 1, we can move on to fixing column 2. When you're attempting to get zeros in column 2, you want to rely on row 2 for all of your operations. So we want to use this 1 to eliminate this 1 and this 3. And we end up with very similar steps. So to fix row 1, we're going to do row 1 equals row 1 minus row 2. And to fix row 3, we're going to do row 3 equals row 3 minus 3 row 2. Both operations utilize row 2. Copy down row 1 and subtract row 2. Be very careful when you're subtracting, especially in this example, we're going to be subtracting a negative. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus -3 is 3. And 1 minus 3 is -2. It's actually my advice to most students. Instead of using subtraction, always use addition and distribute whatever sign you're doing. That way you don't have to worry about the extra step of subtraction. This result is to replace row 1 in my matrix. And we're going to repeat this process with row 3. Row 3 currently is 0, 3, 4, 9. And again, I prefer students to add and distribute whatever value is here. So we're going to distribute a negative 3 to row 2, and that's going to give us 0, negative 3, positive 9, and negative 9. We're left with 0, 0, 13, 0. So from here, we want to fix column 3. And when you're fixing column 3, you really want to be careful that you only use row 3. This problem is super tempting to do row 1 plus row 2, which would cause these 3's to zero out. But what else would happen is this 0 would become a 1, or this 0 would become a 1, because we'd be adding all of the numbers together. The rule of thumb is when you're trying to fix column 3, use only row 3. Well, the first thing I need to do is take 1/13 row 3. This 13 can reduce down to a 1, and now I can use this 1 to eliminate the 3's in the other rows by doing row 1 equals row 1 minus 3 row 3, and row 2 equals row 2 plus 3 row 3. The interesting thing about row 3 is that it doesn't have anything in it other than this 1. So when I subtract this, the only number that's going to change is here, because subtracting 0 does nothing, subtracting 0 does nothing, and subtracting 0 does nothing. When I go to do this row, the only thing that's going to change is here, and I'm ready to read my solution. I have x, nothing, nothing, equals negative 2, y equals 3, and z equals 0. So my final answer for this matrix is negative 2, comma 3, comma 0. The last examples that I want to show you in these video notes have already been solved, and I just want to demonstrate the difference between a dependent system and an inconsistent system, and really hone in on that vocabulary. So example 5 is a dependent system. And when you're solving a dependent system, you'll know you've reached the conclusion when you've zeroed out your bottom row completely. So here we're looking at 1, 1, 2, 30, 0, 1, negative 2, negative 7, and 0, 0, 0, 0. This row, the 0, 0, 0, 0, is what makes this a dependent system. And when you run into a dependent system, you are going to leave your answer in terms of the third variable, or the row that has zeroed out, which is z. So my answer is going to be something, something, and then still say z. Take your system, or your augmented matrix, and rewrite it as a system. So my first equation is x plus y plus 2z equals 30. And my second equation, let me write that smaller, x plus y plus 2z equals 30. And my second equation is y minus 2z equals negative 7. Well, the second equation is very easy to solve. I add the 2z to the other side, and I get y equals 2z minus 7. These equations must be in terms of z. So when I go to solve this first equation, it can't say x and y. I'm going to have to use substitution. X plus 2z minus 7 plus 2z equals 30. And I'm going to solve this for x. Combine like terms, we get 4z. And add 7 to the other side. X plus 4z equals 37. So x is equal to negative 4z plus 37. And this is how we write our answer to a dependent system. We keep an ordered pair or an ordered triplet in terms of the third variable. The last example, no solving is necessary, and the only thing I'm going to change about this example is the final row. In this example, we have a number instead of a fully zeroed out row. What this means when we go to write our equations is that we have x plus y plus 2z equals 30. That's fine. Y minus 2z equals negative 7. Also fine. And then we have 0, no variable over here, equals 6. Does 0 equal 6? No. So when this happens, we end up saying that the system is inconsistent, which is also saying that there is no solution. These lines don't coincide at a single point. This concludes part 2 of the video notes for Objective 4B, Solving Systems Using Augmented Matrices.